Hello everybody, it's Blair here, and today I'll be talking about the applications of the polymerase chain reaction. However, before we can talk about its
in an effort to save time, I will sometimes refer to the polymerase chain reaction as PCR, its abbreviation. With that being said, I think it would be appropriate if we talked a little about the man who invented PCR. His name was Carey Moist. He was a biochemist who won the 1993 Nobel Peace Prize for chemistry for his invention of PCR. And so you might be wondering, what is PCR? And my definition for PCR is a technique that can be used to make a few DNA molecules, to take a few DNA molecules, and produce a large number of copies of those molecules pretty quickly. Just as a quick brush up on DNA molecules, one of the molecules on the bottom, which are called nitrogenous bases, in a ribose and a phosphate group, will all combine to create a monomer of deoxyribonucleic acid, which is called a nucleotide. And in total, PCR typically starts with roughly 15 to 20 nucleotide long strands of DNA. And just as a couple other potentially new terms that I will use throughout this presentation are the PCR machine, which is the machine in which PCR takes place, the primer, which is kind of like a short stretch of DNA that will bind onto the DNA. It'll kind of initiate PCR by binding onto there. And then there's Taq polymerase, which is a type of protein called an enzyme that attaches to the primer, even in extreme heats. And Taq polymerase will be synthesizing corresponding nucleotides as pair for the nucleotides that are already there. So you might be wondering, how does this work? Well, PCR can be broken down into three pretty simple steps. They're going to be called denaturation, annealing, and extension. And the first step is called denaturation because in this step, DNA is heated to around 96 degrees Celsius, and this heating will denature the molecules. And by that I mean the hydrogen bonds, signified by the pink dots on the left diagram, will be breaking. So that's kind of what denatures kind of means here. And this in turn turns a double-stranded DNA into single-stranded DNA, meaning, you know, the two strands kind of just separate because there's no hydrogen bonds holding them together. And the next step is called annealing. This is when DNA is cooled to around 60 degrees Celsius and the primers are added. The primers on the diagram on the right are kind of like the yellow and magenta check marks. And so once two of these primers are added, all the DNA will be put into PCR machine. And third is the extension step. This is where the DNA polymerase is added at a temperature of around 72 degrees Celsius. Taq polymerase is added and it will attach to the primers and eventually go on to synthesize a DNA strand that corresponds with the two separated strands of nucleotide. And this will go on to be the complementary strand. This step will end with two double-stranded DNA molecules, which are both identical to the strand that we started with at the beginning. This process can be repeated, and the amount of strands will be doubled each time. So, although PCR is technically possible without them, you can often see buffers being used with PCR in order to try and optimize the productivity of the PCR. Common buffers are the K+ ion from potassium chloride and the ammonium ion from ammonium sulfate. The K+ ion kind of serves the purpose of promoting the annealing step talked about in the previous slide. And this is kind of when the primer was attaching to the 3 end. And the K+ will further stabilize the molecule and kind of allow those primers to attach more easily. And this happens because the positive K+ ions will negate the destabilizing effects of having such a dense negative charge from that phosphate ion in the DNA molecule. And the NH4 works on the hydrogen bonds holding the DNA strands together. as you can see, it kind of just destabilizes the bonds and makes them easier to break, which is obviously, as I said in the previous slide, one of the goals of a part of PCR. You want to break it apart during the denaturation phase. So what are some processes that are kind of used with PCR, since so far I've kind of just explained copying DNA. And one that is very commonly used with PCR is the Sanger method of DNA sequencing. And this process is actually very similar to PCR. It has the same steps, you know, annealing, it's got denaturation, it's got extension, it's got all those. But there are a few key differences that kind of make them different. And one is the overall goal. And for the DNA sequencing, the goal is to figure out the composition of DNA in the order of the bases rather than just to make copies of them. And this is achieved by making the change that there are both the deoxynucleotides, which are kind of just nucleotides I was talking about in the previous slide, and dideoxynucleotides, which are kind of different. As you can see in the graphic on kind of like the top left, there's a missing H where the hydroxide was. It's just another H, and hence the name dideoxy. And this has some effects, one being that the color changes, and another being that, as you can see in the bottom right, kind of pointing in it with an arrow to how that bond that holds together the bases, it has the hydroxide in it. So taking that out kind of doesn't allow for the molecules to bond anymore. And these are taken advantage of in the method because, as you can see in my example here, it will kind of cut a molecule short because there's no hydroxide there. It can't go any further. No more nucleotide pairs can be added. And there's colors. So these are all taken advantage of, and there's another process after the Sanger method called Joe electrophoresis, where due to DNA being negatively charged, they put it on the negative electrode on the kind of bottom of the diagram, and the smaller molecules move more quickly towards the positive electrode, and they'll move further down, and then you can kind of stop and observe, and depending on how far it went, you can kind of tell which DNA is shorter, which one's longer. And in this context, this is useful because you can kind of try and figure out where the dideoxy nucleotides were added, because obviously it being added earlier on made it shorter. And using this, they can figure out base by base by base which dideoxy nucleotide was where, and they can figure out which dideoxy nucleotide it was by color. Just to clarify, any dideoxy nucleotide would cut it off. They need the color to clarify which specific one it is. So one very popular use of the polymerase chain reaction is in forensics, specifically DNA fingerprinting. Although you might be looking at the outcome on the bottom left, that's possible, but the one on the bottom right is kind of a more accurate use. PCR and gel electrophoresis are not really used in DNA fingerprinting to prove which suspect's DNA was there. It's more of a process of eliminating subjects, kind of used in the beginning stages of an investigation. And because even if there's only one piece of DNA that differs from the DNA at a crime scene to a suspect's DNA, then that suspect can be ruled out. And another use of PCRs was in the Human Genome Project, which was a project from 1990 to 2003. And according to the National Human Genome Research website, the Human Genome Project was, and I quote, was the international collaborative research program whose goal was to complete mapping and understanding all of the genes of and understanding of all the genes of human beings. Sorry. And the polymerase chain reaction was an integral part of this process because the millions of copies of DNA they were able to produce enabled them to study each piece of DNA with a lot of depth. That's in large part thanks to the extensive amount of research they can get out of one molecule from the polymerase chain reaction. So I've really only mentioned a couple in this kind of presentation here, but there are many more uses for the polymerase chain reaction beyond just what I've mentioned. Because if you think about it, the ability to make millions, billions of copies of DNA in minutes makes all types of things possible and way more accessible. Some more interesting applications where they in iceberg, or I don't know, they found some woolly mammoth DNA frozen somewhere, and they were able to analyze its DNA, even though it was kind of damaged and very limited. They were able to make a bunch of copies of it and kind of study it more. And another one is they were able to identify a bunch of people, as you can see, and just some real some of the things that really contribute to PCR being as widely used as it is that it's extremely quick, it's cost effective, and it works even with partially damaged DNA, and also it works for all types of plants and animals. As for the disadvantage, if you remember from the fourth slide, I was talking about how buffers and exact temperatures are needed. However, I was not trying to say that at those perfect conditions, that means it is given that the molecules will cooperate. Sometimes they do not. In addition to this, a lot of stuff can go wrong. Just to give a few examples, there can be an improper sample collection. There can be an insufficient amount of the specimen. The DNA can be degraded beyond repair during shipping or storage. The presence of amplification inhibitors in the specimen, and also laboratory processing, testing errors, contaminants used during specimen collection, transport, or even processing. And final kind of limitation of it is that I might have made it seem like it does a lot more than it does in this presentation. Just to clarify, PCR is it's just like a photocopier. It just makes copies of things. It doesn't make anything new. It just creates a lot of something that can be further investigated.